Okay, so 2022 IMO 6. Okay. The last question on this year's IMO, which happened last week. Okay. The closing ceremony was literally like 2 days ago. Okay. The question was like this. If you have an n by n, it's actually a Norway square or something. Norwegian square. There's like a 3 by 3 block, yeah? There's 9 squares. And then you write the numbers 1 to 9 somehow, right? In the squares. Okay. And the question asks you for essentially what's the number of uphill paths.
Well, you said that.
Yeah. So what is an uphill path? So an uphill path starts always at a valley, okay? So a valley is something where the number is smaller than all the numbers next to it, okay? So numbers are next to each other if they share an edge, yeah? Okay. And so the numbers are next to each other if they share an edge. And so the path could go from, it could start at 1's a valley, yeah? Okay, and for it to be an uphill path, it means that every number it goes to has to be bigger than the previous one, yeah? So it goes here, it could go to 3, yeah? And then it could go to 9, okay? But 9, I guess, it can't go any further. Because it's the highest.
If 1, 2, 3 is 1, do you count 1, 2 as well?
Yeah, so you also count 1, you also count 1, 2, you also count 1, 2, 3, and you also count 1, okay? So that one uphill path from 1, 2, 3 to 9 actually gives you 4 uphill paths, okay? Does that make sense? And the question asks you, so given the grid size, so n, so this is 3 by 3, okay? Given how big the grid is, find the minimum number of uphill paths possible. So you gotta give a numbering of the grid squares. So for example, if I number this grid like this, right? Okay. The question is how many uphill paths are there? Okay. So for example, if I start at 1, I could go 5, I could go 1, 3, 5, and I'd be stuck, yeah? Or I could go to 1, 9, and I'd be stuck, yeah? So that's a total of 1, 1, 9, 1, 3, 1, 3, 5. That's a total of 4 uphill paths, yeah?
Yeah.
Yeah, I think the good thing about Combi is the questions are always, you can understand what the question's asking. And the solutions are usually you can understand them, even at a much lower level than being able to come up with them. Okay, so is that the only valley though? Can you see 2 is also a valley, yeah? Okay. 2 is also a valley. So it can go 2, 4, 6, 7, 8, 9. Or it can go like 2 straight to 7. It can go 2, 4, 5. Or it can go 2, 3, 5. Yeah? Or I can go like 2 straight to 7 or 2 straight to 9, yeah? So you have 2. 2 goes to 4. 2, 4, 5. 2, 3. 2, 3, 5. You have 2, 4, 6. 2, 4, 6, 7. 2, 4, 6, 7, 8, 2, 4, 6, 7, 8, 9. And then you go straight to 9, 2, 3 to 7, 2, 7, 8, 9, 2, 7, 8, 2, 7. We can go straight to 9, yeah? So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, yeah? So that's saying this function which takes 3 to the minimum has to be at most 17, yeah? That makes sense? Okay, so I am going to try to describe a little bit about how we solved this solution. We solved this as a team with a bunch of people in the holidays, and went something like this. Okay, so we started with some small cases. If it's just one, you can only put one there, right? And there's only one uphill path, yeah? So we know f of 1 equals 1, yeah? Okay, f of 2. So you don't have that many cases. You can do 1, 2, 3, 4, yeah? So it only counts so like if you did 1, 2 on the bottom like this, it could still be the same if you put 3 and 4. So it's only if it's like 4 and 3 that would be different, yeah? So now, but this is actually the same as that, yeah? Because it's just clockwise and anti-clockwise, 1, 2, 3, 4, yeah?
Yeah.
That's really just the same case. And I guess fundamentally it would be different if the 2 was not next to the 1, yeah? And then the 3 and the 4 could be in either way and it'd be the same. Okay. And then another case would be if 1 was not next to the 4, yeah? So if it was not next to the 4, it'd be a 2 and 3. So there's really only 3 cases based on what it's not next to, yeah? Okay, so then we count the number of paths for each, right? There's only one valley in this one, it's a 1, yeah? There's actually 2 valleys in this one. There's only one valley in this one. So you notice that the valleys, there's only one valley if the 2 is next to the 1, right? But if there's 2 valleys if the 2 is not next to the 1. Okay. So you get, yeah, so we should say we solved this as a team live. Yeah, we recorded the solve as well. We didn't, maybe over several parts, but the recording is a bit long. This is more like a recap of that, yeah? So this is not being solved right now, it's being recounted. Okay, so it goes, we could go, so this could be like 1, 2, 3, 4, yeah? It could be 1, 2, 3, 1, 2, it could be 1, and then it could also go 1, 4 straight away, yeah? See that? And here, it could go 1, 1, 3, 1, 4, 2, 2, 3, 2, 4, yeah? And here, it could go 1, 1, 2, 1, 2, 4, 1, 3, 1, 3, 4, yeah? So you notice that f of 2 equals 5, okay? Because 5 is the least you can get. And you get 6. So there's sometimes you get 6, and notice you get 6 when you get 2 valleys, yeah? And so you suspect that you might get less when you get less valleys, and the reason is probably because um, when you get a valley, like you have to count the valley as a separate path, and you count the paths coming out of the valley, right? Whereas if 2 was just like a destination, it could end at 2 for one way, it could end at 2 the other way. Yeah, you wouldn't have to count the endpoint 2 separately. So it kind of makes sense that the more values you have, the bigger your number is. Okay. Okay, so f of 1 equals 2, f of 2 equals 5, f of 1 equals 1, f of 2 equals 5. So it's actually not that easy to figure out what f of 3 is. Okay. So if we just take some random, let me think. If we take some kind of, if we take the value in the middle, make sure there's no other values, so the 2 is connected, the 3 is connected. Okay, we'll do something like this. 4 and 5, yeah. Okay. You get, it could start at 1, and it can only start at 1. Okay, it's the only value. So then it could go 1, 2, 6, 1, 2, 7. It could go 1, 5, 9. I could go 1, 4, 9. I could go 1, 3, 6. I could go 1, 4, 8, 1, 3, 8. Okay. So basically 1, 2, 6, 1, 2, 1, 2, 7. So there's basically like, it's symmetric in each direction, yeah. It is not a Schwarzenegger. Okay, so 1, 5, 7, 1, 5, 1, 5, 9, and it's 1, 4, 9, 1, 4, 1, 4, 8, 1, 3, 6, 1, 3, 1, 3, 8. Yeah?
Yeah.
How many is that? 6 plus 7, yeah? That's 13, yeah? Okay, so f of 3 is at most 13, okay? Well, it's kind of difficult to get that it was equal to 13, okay? Because there's so many combinations. How do you know you haven't missed one? And we kind of kept looking, but they all turned out like we couldn't get anything less than 13. We got 13 a bunch of times, yeah? And so if, and we also actually had this nice construction, was that if you had a square, you can make like a checkerboard pattern. And you could put all the big numbers in the black squares, and you could put all the small numbers in the white squares, okay? And because every white square is surrounded by black squares, then that means like the white squares are all valleys, okay? And that it always means, and the black squares are all peaks, okay? And so the valley always ends up at a peak in the first step, and so it can't continue the path anymore, right? So this is a very easy example to calculate lots of bounds, okay? So for example, here, I think you get that like f of n is less than n cubed or something for sure. Okay. So the next step was like, okay, I think it was even some quadratic. So it was less than some quadratic as well. Yeah. And so then we took a bit of a leap of faith and said, well, what if f of 3 was 13? Okay. Okay. Then what kind of pattern is this? Okay. So we got that 1 is actually 0 squared plus 1 squared. 5 is 1 squared plus 2 squared. Yeah. 13 is actually 2 squared plus 3 squared, right? And so a sort of a conjecture was that Fn was n minus 1 squared plus n squared, right? And it kind of agrees, sort of, if this was the case, it would also be a quadratic, yeah? It wouldn't be a cubic. So it kind of agreed with this. And we could write this as 2n squared minus 2n plus 1. Yeah? Okay. So So here's the next interesting development. Is if you count, if you take a grid, right, and you count the number of edges, okay? So here there's 1, 2, 3, 4 edges, yeah? Okay. Here there's 1, 2, yeah, so there's 4 edges for 2 by 2. There's 0 edges for 1 by 1, yeah? There's 0, 4. If you count 3 by 3 edges, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, yeah? Did I miss one? I missed this one, yeah? It's 12, yeah?
Yeah.
Good, he's paying attention. I like this. 12 edges, yeah? So you notice the number of edges. The number of edges. The number of edges in the grid, okay, is it's always one less than the number that we had, right? So we had 1, now we got 0. We have 5, now we have 4. We had 13, now we have 12, yeah? So if you think about an m by n grid, how many edges does it actually have, right? No. So it has it's like matchsticks, right? It has like so it has 1, 2 up to n across, but you don't count the top one. Okay. You don't count the bottom ones. You only count the middle sort of these ones. 1, 2, 3. So the things between the edges. So there's n minus 1 of those, right? There's n minus 1 times n, and obviously there's another n minus 1 times n vertical ones, yeah? So there's 2 lots of those, which is 2n squared minus 2n, right? So there's literally always one less edge, one less edge than there are these values, right? Okay. So what if we could somehow argue that like there was somehow as many paths as there are edges, yeah? Then we could prove that those numbers are equal or close to being equal, right? Okay. So then what happened was this. So if you have just a random grid, so maybe this one we had before. Oh, just erased everything. Okay. Okay, what was this one? One, we're missing a 4, yeah? And a 8. Okay, so we're trying to see how does the edges correspond to paths, right? Okay, so if you take this edge here, yeah? How does this correspond to a path, yeah? Well, what can you do? You can go... Okay, the path can't go past 6, right? So 6 could be the end of the path, yeah?
Mm.
Okay, but then there's only one direction it could come from, it's the 3, right? Okay, from using this edge, it could only come from 3, yeah? Okay, and then 3, where could 3 come from? Oh, okay, it's actually already a valley, right? It can't go anywhere. So this would be the path that corresponds to that edge. See? Um, okay. What if you took this edge, 6? Yeah, you could start at end at 6, come from 2, right? But 2 is a valley, yeah? So this actually corresponds to 6, 2, or 2, 6. Okay, what about this edge? This edge corresponds to 2, 7, okay? And this edge corresponds to 7, 5, but it could also go to 4, right? Back to 1, yeah? Go to 3, yeah?
Yes.
So the point, I guess, is that if from every edge you can make at least one path, yeah, one uphill path, by basically kind of going downhill from the edge, yeah, then there's at least as many paths as there are edges, right?
Yeah.
So what that proves, the number of paths is greater than f of n is greater than or equal to 2n squared minus 2n, right? Does that make sense? So there's at least as many, and so you can see the problem is if there's more than one valley, like 4 could go to different places, right? Yeah. Yeah, and actually, if you don't count the valley itself, because you always get one from the valley, right? And the valley doesn't really correspond to an edge, right? So that's where the +1 comes from. It's the valley, you know. So basically, what you're trying to do. So actually, you prove now that it's always the actual answer is always bigger than or equal to 12. Okay. Okay, and since you actually haven't even counted the valleys, it's actually greater than or equal to plus the number of valleys. Yeah. So wait. Um, yeah. So if there's always at least one valley, right? So then this is always greater than or equal to 2n squared minus 2n plus 1. Okay, and so that proves that the answer here actually is 13. Okay, so that's one sign of progress, is you're able to prove something that you couldn't prove before. Okay, because that shows f of 3 is at least 13, and we know it's a most 13. Okay, so this is very good. So then you can see if we can prove it's at least 2n squared minus 2n plus 1, okay? How do we prove it's equal, okay? So we just need to number the grid in a way that that sort of gives us just one path for every edge, right? And not multiple paths. And that it only has one valley, okay? Right, because if it only has one valley, then you only plus 1, right? And if it has one path for every edge, then you'll get exactly the right number, okay? So what does that mean, okay? So why did this one get 13? So why did this one get 13? Which one was the one that got 13? Did I erase it? Had a 1 in the middle. No, I mean, it doesn't really matter. I can just do it again. Okay, so this is my valley, right? Okay, so 1, 2, 3, 4, 5, like 6, 7, 8, 9, yeah? So the way this kind of works is there's only one valley, right? And that's at the start, yeah? Okay. And the nice thing about this thing is that there's exactly one way to go back to the valley. Okay. So, for example, if I start at so these are what's called peaks, right? Yeah. So peaks always have multiple ways to get back to the valley, right? Because peaks um are bigger than anything that's next to them, so they can go anywhere they want, right? But the thing with peaks is whatever way they want, they have to use one of these edges, right? Yeah.
Yeah.
So it's still each edge corresponds to a way because the two ways of getting from a peak has two edges. Yeah. Okay. But once you're off a peak, like you're at the 3, right? There's only actually one way to get back. See, so you can only go back one way. Yeah. Okay. So that's why those two blue edges correspond to those two parts. Yeah. And these red edges correspond to these parts. Yeah. Okay. And similarly, from the it's symmetric. Okay, there's 4 peaks. They're all symmetric. So that means that there's only one path for every edge, right? And so basically, um, so this thing you probably won't know at the moment, but when you have a graph, okay, and there's only one way to get from each vertex to another vertex, yeah, then that graph is basically called a tree. Okay, so for something to like that to happen, like if there's always a unique way to get from one point to another, okay, it means there can't be a cycle. Okay, so for example, if it could go that if this was destination and this was the starting point, right? If it could go this way and then go here, right? And it could go so if there's two ways to get to the 2, right? Can you see that always creates a cycle? Okay. So you just go back one of the ways and you can go around this as a cycle. Yeah. So a tree is basically defined to be like a graph that has no cycles and is connected. So as a consequence of having no cycles is a unique way to get from each point. Okay. So then to number the grid the way we want it to, okay, um, to number the grid how we like it, we just need to do it in a way that creates no cycles and make a tree. Okay. So for example, if we had a 4x4 grid, okay, and I want to put my valley here, right? This is my starting point. Yeah. That's like my 1. Yeah. Okay, I want to do something that gives me a tree and keeps everything connected. So for example, I could try to connect this to here, right? I could connect this to here, to there. Let's talk. Maybe not quite working like that. So I want a tree. Okay, maybe I can try going up the top then. Around. That's still not so good. Go like here. No, you don't have to even start in the corner. You just need to make a tree using the grid squares, you know? So let's see. I'll do something like this. Like that, yeah? I think that's a tree, isn't it a tree? Okay, so what I mean by that, I want the red spots to be the like the small numbers, and I want the blue spots to be the peaks. Okay, so to make that possible, so there's 16 numbers. I just need to make the biggest numbers in the blue, right? So it's like 16. For some reason I associate big numbers with dark numbers. 14, 13, 12, yeah? Okay, and then I just have to I can put the one anywhere, okay? I can put the one like here, yeah? And then I just kind of gotta like I can pretty much do anything. I just make sure it all connects up, yeah? So 4, 5, 6, 7, 8, 9, 10, 11. Yeah? So basically I label the red stuff anything I want. I label the blue stuff um the next highest numbers. Yeah, so the blue stuff I can count from n squared down, and for the red stuff I can go from 1 up. Yeah? And obviously it'll use up all the numbers. Okay? And my claim is this gives me what's n minus what's 3 squared plus 4 squared. This should give me is less than 25. Yeah? Okay, so the way it works is you take any edge. So let me take this edge, okay? And that edge is coming from the peak 15, right?
Yeah.
So I just take the path that ends at 15, goes through that edge to 7, right? And there should be a unique path from 7 back to 1, okay? Okay, and so it has to follow the red line, yeah? You see? See how that works? So it goes 7, 4, 3, 2, 1, yeah? Yeah. Okay, if I want to talk about this edge here, that's path ending at 14, coming from 9, 8, 7, 4, 3, 2, 1. Yeah? Okay. Um, yeah, so you can just pick any edge you want. So even an edge that's not connected to a peak, yeah? What if like this edge, yeah? Then the path ends at 10 and just go back 8, 7, 4, 3, 2, 1. Yeah? So the whole point is there's a unique way to get back to 1 on any of the red, along any of the red, right? And there's a unique edge that goes from a peak to a red square. Yeah. So then, so so basically, it amounts to like if you can draw a tree in such a way that you know the non-tree squares don't disconnect the graph, right? They don't disconnect it. Then you can solve the problem. And then the answer is always 2n squared minus 2n plus 1. Okay, so I think I have some diagrams here from before that I think Yasser drew some of these. So if you look at the spoilers here. So this is a picture of the 20 by 20 grid, yeah? And you have this pattern where it's basically like this final boss is not as hard as I guess the insight of coming up with the bijection thing, which I guess is sort of due to high being. So okay, so if can you see that so the green X's represent, the dark blue patches we had before, right? And the red lines, well, we were using red lines already, so you know what that represents. And Josh wakes up from hibernation. Did I hear boss? But I thought, wait, it wasn't the meme or the story was that Josh wasn't good at video games, so he would never get up to the boss. Okay, so see the red lines. So basically, the pattern can you see is like if you basically just have one vertical thing connecting all the horizontal branches, yeah, and if you and then if you have the horizontal branches kind of in this pattern, it'll be spaced out enough to get everything, I think so. This will work for like any n, okay? And then so basically you just have, like so the second row is just all red, yeah? The third, fourth, fifth row is all red except for one. Then the sixth, seventh, eighth row is all red. 11th is all but one, yeah? So every two mod three, it's all but either the one at the end, okay? And then um and obviously depending whether it's you get all the way to the end or not, then the vertical line is determined, right? So it kind of goes up, around, up, around, up, around. Yeah. And that is it. That solves the problem. Okay, so it seems pretty easy, don't you think? For the last question, the final boss, the last question of the IMO. So it sounds like you go to IMO, you get into AMO, you get into the team selection test, you get into the IMO team, and then you go to the IMO, and this is the last question. Okay. So maybe how many people do you think solved this problem?
20.
20? Well, um, actually pretty close, so can't really continue this discussion much further. So you look at the stats, problem 6, 22 people solved it completely out of all the people that went. So there was 600, maybe 500 and how many people how many people total? Um, Usually you can tell how many people total by how many people got so if you look at so it's the sum of the column, right? So if you add up the P6 column, then you get roughly 580 people. So 450, 550, 570 something, 580. Yeah, so maybe 580 people did the test, and 22 people got 2 points, and 22 people got 7 points. 2 people got 6 points. Lots of people got 4 points. And actually, if you get 1 point on this question, assuming you got all the other questions except for question 3, you get a silver medal. That's the silver medal cutoff. Okay, if you got 4 points on this question, so if you got 3 points on this question and you got 3 points on question 3, yeah, these are out of 7, these questions, then you'd be at the gold medal cutoff. Okay, or if you just got 6 points on this question and no points on question 3, you'd be at the gold medal cutoff. Yeah. All right. What do you guys think? Do you have any questions?
So bolts.
Yeah. So even the final boss of this contest was only using like the most basic thing in graph theory. It was trees. And you probably didn't even need to know much about it to actually do it. Um, okay, 4 decents, 1 very good. I mean, this is the kind of thing I would expect sort of junior and intermediate people to be able to understand, even if they couldn't come up with the solution themselves. Okay. I mean, ironically, there are aspects of question 5 that you probably won't be able to understand the solution of just because. Oh well, I mean, at least not instantly. Okay. Um, requires some more more fiddling. Okay. Do you have any questions about this? Do you enjoy this topic? So question 1 was also combinatoric. So if you're interested in seeing what question 1 was like, that was like the Saturday class video. So you can request the video and then you can watch that. Neutral. What does neutral mean? Awesome, neutral, enjoyable. 2 enjoyables, 1 awesome, 2 neutrals. I feel like if you say neutral to some of this, it does mean that you don't necessarily understand it. But then you said decent to understanding, which is quite the paradox. Alright. Shall we move on? Any questions? Did you enjoy this? I think if you understood it, you enjoyed it. Alright.